Hello everyone, my name is Rajni Dhakal from Namchi Government College, Department of Physics, and I'm going to explain velocity addition and mass energy equivalence. First of all, I would like to thank the Department of Physics of Namchi Government College to give me such an opportunity to make video and upload it on YouTube. First, first we have velocity addition theorem. Here we have studied the Lorentz transformation earlier. Here the position transformation, that is x dash is equals to x minus bt upon under root of 1 minus v square by c square, and y dash is equals to y and z dash is equals to z, and the time position and the time transformation is t dash is equals to t minus xv upon c square whole upon under root of 1 minus v square by c square. So here first we will know what is v, what is x dash, and what is c. So we are talking about two inertial frames. One inertial frame is S, which is at rest, and another inertial frame is S dash, which is moving with a velocity v at pos at positive direction x. At any point P, if we are seeing an object from S frame, त्यसको coordination चाहिँ हुन्छ x, and S frame को बाट हेर्यो भने त्यसको coordination हुन्छ x dash. And here v is the velocity of frame S dash with respect to S, and here c is the speed of light, as we all know that. As we have discussed that from the Lorentz transformation equation for position and time, we get x dash is equals to x minus vt by under root of 1 minus v square by c square, and t dash is equals to t minus xv by c square upon under root of 1 minus v square by c square. So on differentiating both the expression, we get dx dash is equals to dx minus v dt by under root of 1 minus v square by c square, and dt dash is equals to dt minus v dx upon c square by under root of 1 minus v square by c square. Here v and c is not getting differentiating because they are constant, as v is moving with a constant velocity and c is the speed of light. So now velocity of the particle p with respect to the observer in frame S will be u equals to dx by dt. We have to differentiate the displacement with respect to time. U equals to dx by dt. We have to differentiate this position with respect to time. Velocity of particle p with respect to the observer in frame S dash will be u dash is equals to dx dash by dt. As we already know that the velocity of particle p with respect to observer in S frame is u equals to dx by dt. So we know the value of dx dash and dtx, as we already calculate it in equation 2. So on using equation 2, we get u dash is equals to, by putting the value of dx dash, we get dx minus v dt by dt minus v dx by c square, which is equals to, so on dividing both numerator and denominator by dt, we get dx by dt minus v upon 1 minus v by v dx by c square dt. As we know that from equation 3, dx by dt is equals to u. So on using equation 3, we get u dash is equals to u minus v by 1 minus uv by c square. So that is equation 5. Now, using condition of inverse transformation, we replace u dash by u and u by u dash, and plus by minus and minus by plus. So the equation 5 become u equals to u dash plus v upon 1 plus u dash v by c square. There are three different cases in equation 6, that is, case number 1, if u and v are very small compared to c, then from equation 6, u dash v by c square is negligible as they are very small as compared to c. Therefore, the equation will become u dash is equals to u minus v. So the result is same as predicted in Galilean transformations. In case 2, if u dash or v is equal to c. Okay, so if u dash or v, let v is equals to c, then equation 6 become u equals to u dash plus c upon 1 plus u dash by c is equals to u dash plus c by c plus u dash into c is equals to c. This case 2 shows that if the frame or object moves with the velocity of light, then the relative velocity is c, whatever may be the velocity of the other. This result is consistent with Einstein's second postulate of special theory of relativity. In case 3, suppose the frame S dash moves with the velocity of light and the object moves with the velocity of light in this frame S dash, that is u dash is also equals to c and v is also equals to c, that equation 6 becomes u equals to c plus c upon 1 plus c square by c square equals to 2c upon 2 is equals to c. This shows that when velocity of light c is added to the velocity of light, then it merely reproduces the velocity of light itself. Hence, we said that the velocity of light is the maximum attainable velocity. So our next topic is mass energy equivalence. As Einstein already gave us that E equals to mc square, we are seeing this equation since from our junior classes like 10, 11, 12. So now today we are going to derive this equation. First of all, let us discuss what is this. So the mass energy equivalence relation is E equals to mc square. It is the most famous and most significant relationship obtained by Einstein from the postulate of special theory of relativity. Numerous experiments have demonstrated and the mass is convertible into energy and energy into mass. The conversion factor between two is the square of speed of light. The only conversion factor between this is the square of speed of light. The mass energy equivalence can be deducted directly from special theory of relativity. So let's start with the derivation of Einstein mass energy relation. So from work energy theorem, GW is the amount of work done by the external agent, and decay is the increase in the kinetic energy of body, and work done is equal to the force into displacement, that is in the dot form. So from Newton's law, F is equals to dp by dt, where p is the momentum. We also write p is equals to mv. So in place of p, we are writing ddt by mv. So on differentiating equation 2, F is equals to m dv by dt plus v dm by dt. For this differentiation, we have to use the product function of differentiation. Here, first we have to write this first m and then differentiate the second term, and first write the second term and differentiate the first term. So on further, we see that dk is equals to m dv by dt. Here that is, there is f is equals k, dk is equals to f dot ds. So we are substituting the value of f and multiplying it ds. So m is equals to dv by dt ds plus v dm by dt ds, which is equals to m. We are writing ds out here and dv out here. So m is equals to ds by dt into dv plus v ds by dt into dm, which is equation 4. So on rewriting equation 4, we get ds by dt is rate of change of displacement, that is velocity. So we are writing ds by dt as v. So the equation 4 becomes dk is equals to m, in place of ds by dt we are writing v, and again dv plus, there is already one v, and ds by dt is also v, that is v into v is v square dm. That is equation 5. Now from the relation between mass and velocity, m is equals to m naught by under root of 1 minus v squared by c square, which is equals to m naught 1 minus v squared by c squared to the power half. On differentiate these two, and this 2 is getting cancelled, and this minus is also getting cancelled and having plus. So the result come m naught v dv upon c square on under bracket v square by c square to the power 3 by 2. That is equation 7. On using equation 6 in equation 7, we get, so now we will split this c square under bracket v square by c square to the power 3 by 2 on 1 on under root of this term and other as this. So as we know that m is equals to m naught by under root of 1 minus v square by c square. So here one become, in term of that, m is हामीलाई याद छ m equals to m naught by under root of 1 minus v square by c square. So हामीले 1 minus v square by c square to the power 3 by 2 लाई एउटालाई लेख्छ under root of 1 minus v square by c square, अर्कोलाई लेख्छ 1 minus v square by c square. So m naught by 1 under root of 1 minus b square by c square, we will write m, and other term will remain as same. So in denominator the term is remaining c square 1 minus b square by c square. We are multiplying c square with 1 and we get dm equals to mv dv by c square by v square. So on rearranging equation 8, we are cross multiplying this dm with c square minus v square and mv dv with 1. So it becomes mv dv is equals to c square minus v square dm. So on placing the result of equation 9 in equation 5, we get dk is equals to c square minus v square dm plus v square dm is equals to c square dm. Dm is getting multiplied with c square dm and minus v square dm. So it becomes c square dm minus v square dm plus v square dm. This two is getting cancelled and we get c square dm. On integrating both sides of equation 10, we get k equals to integration of dk is equals to, we have to differentiate this dm. We have a lower limit m naught and upper limit m. C square dm, which is equals to c is constant, so the integration of dm is m minus m naught. On placing the value of equation 6 in equation 11, we get k equals to c square m minus m naught is equals to c square. We are replacing the value of m, that is m naught by 1 minus v square under root of 1 minus v square by c square minus m naught. On further solving equation 12, we get E equals to m naught c square plus m minus m naught c square is equals to mc square. Here also m naught c square plus, we are multiplying this c square with m and m naught. We get m naught c square plus m c square minus m naught c square. So this m naught c square and minus of m naught c square get cancelled and we get m equals to mc square. So we can conclude the famous Einstein mass energy equivalence relation as E equals to mc square. Now we have last topic, that is massless particle. If any particle is having zero rest mass, then such particle is said to be massless particle. From the relation between energy and momentum, we have E is equals to root over m naught square c to the power 4 plus p square c square. For any massless particle, we have m naught is equals to 0. So E is equals to pc, or p is equals to E by c. Since E is equals to mc square, using equation 3 in equation 2, we get v is equals to c. So we conclude that velocity of massless particle is same as the light in free space. Thank you.